Welcome to the second installment in our 2022 webinar series. I'm Julia Speaker, Project Manager and Cast It Team Lead in the American Metal Casting Consortium's Innovating Casting Technology Program. Cast It is an acronym for what we do, Casting Advanced Systems Technology Integration Team. Our webinars are funded by the Defense Logistics Agency. What's new in this 2022 webinar series is the project management by a new awardee that precedes the manufacturing engineering of the casting processes in a legacy casting launch, especially in the context of a cold start new awardee who is a machine shop. In the 2021 webinar series, we focused on preparation for successful first article approval of a DLA legacy casting, and we coined the term cold start. For a new awardee attempting a successful DLA legacy casting launch, a cold start is especially difficult because of all the prior successful manufacturing engineering of the tooling and processes has been lost. A cold start is difficult enough for a metal caster familiar with the nuances of casting tooling construction and casting manufacturing processes. It is even more difficult for a machine shop whose core business is very different. The difficulty is relevant because machine shops are now 70% of DLA's new legacy casting awardees. Cold start also means that prior approved metal casting sources are no longer available or may no longer be willing to produce the casting, and the casting tooling as well as machining fixtures are lost and not available. To address this steep challenge, our 2022 webinar series is focused on initial thoughtful manufacturing planning before any tooling is designed or manufacturing processes are chosen. The initial thoughtful planning is called project management. The essence of project management is to clearly identify all that is required in the finished casting, understand it, and put all the major steps in a timeline. The idea is to think of everything that matters in advance and not miss anything. The objective is to not back up to fix or redo anything. For complex, high-specification DLA legacy castings, not missing anything and not backing up to redo anything is a tough challenge. In part one of our four-part webinar series, we addressed a machine shop's awardee's logical first question. Can we machine this geometry complete from a wrought bar or block of an equivalent alloy rather than procure a casting and machine a few of the casting's features to net shape? So in part two, we acknowledged that a machine casting is required, and we addressed the project management issues of planning for a casting made in the air-set sand process. For DLA legacy castings, the air-set sand and investment casting processes are the most capable of the methods to produce the castings. Sometimes either process can be chosen. Other times, one is preferable or even required over the other. The reasons for the air-set sand process choice were addressed in part two. Now, in part three, we address the reasons to choose the investment casting process and how to do the immediate project management planning to assure a successful result, rather than to just start in the usual way. So starting off our characterization of the investment casting process will be our Cast It teammate, Mike Gwynn. Mike is our expert on casting design and manufacturing engineering, and Mike has a background in manufacturing operations management, which includes project management. His focus will be on why to choose the investment casting process, and he will explain the manufacturing engineering considerations for maximizing the surface accuracy and surface finish of investment castings, which is their greatest attribute. Following Mike will be Gary Burrow, our Cast It expert in mold cavity design, which includes tooling design and construction. Gary is also our expert in the additive manufacturing alternatives to traditional casting tooling. Gary will use his expertise in both arenas to explain a case study. His example is a high-specification, safety-critical legacy investment casting that is used as a replacement part in an amusement park roller coaster vehicle. This 10-piece order for a 1970s-era replacement casting has suffered a series of non-conformances and restarts that are typical when a complex casting manufacturing project just starts without project management forethought. But first, Here's Mike with a summary of the indications for and capabilities of the investment casting process.
The investment casting process is one of the oldest, if not the oldest, of all metal casting processes. Yet it probably is the least understood by casual designers and users of castings. Let's take a moment to define a couple simple yet interesting facts about the investment casting process. Historically, it was called the lost wax process, which is really a more descriptive name. From its historical beginnings, artisans would carve blocks of wax into shapes that became the pattern for a casting mold. The mold was made of clay and the type of clay that can be heated to make pottery. When the shell of clay around the wax was heated, the wax melted out or was lost. The earliest lost wax castings were poured in gold and silver. Later, bronze was used, which is like gold and silver, and it's naturally occurring as a metal. Back then and continuing today, artisans carve wax to make bronze statues and fine jewelry. Here's a video that summarizes the investment casting process as it has advanced in today's technology. The video will stop short of the latest technology, which is printing wax substitutes, wax-like polymers, and even wax itself in 3D printing technologies, forming the pattern shapes directly from solid models. In Gary's upcoming case study, two of the important 3D printing technologies are part of the story. The normal process to make wax patterns for investment castings is to machine a die from aluminum into which liquid wax is poured. Then the wax solidifies, becoming the pattern for the investment casting. You will see how that works in this video.
Here's a description of how the investment casting process works. And we see wax patterns assembled on a tree, and those wax patterns become the casting shown over on the right. The tree is sequentially dipped in a powder bed and then coated repeatedly with a pre-ceramic slurry, and the layers then of the ceramic shell are built up so that you wind up then with what we call a ceramic shell investment cast mold. And that's what we see here. The shell is built up repeatedly in that bed of ceramic particles with the pre-ceramic coating on the shell's prior layers. When the pre-ceramic shell is dried, it is turned upside down, put in an autoclave, and the wax is melted out. Then the empty mold is put into a furnace where it is turned into a ceramic, and while it is still hot, then the castings are poured. And one of the great attributes of the investment casting process is fine detail and thin walls, and the hot mold enables that. As we can see, the mold is going to be poured now while it's still hot, so the ladle arrives quickly to take advantage of the pre-existing mold temperature. And you'll see the pouring crew take steps to take advantage of that temperature even after the mold is poured. So we see a filter being removed from the sprue, and you'll see an insulator being applied to one side of the mold geometry and a hood placed over the entire mold. Finally, the shell is broken away from the castings.
Let's take those steps in the ceramic shell investment process and bring them to life with an animation. First, we have that die that creates the wax patterns. Wax is warm and slick, so it will release from the aluminum die with minimum, sometimes no draft. However, there is contraction in the wax and ultimately contraction in the alloy when poured. So there are two contraction rates that have to be designed into the tooling, and Pattern Maker's contraction is a concern in the design of the tooling to make sure that the dimensions, although extremely accurate, are centered within the specified tolerance band. In addition to the accuracy of the ceramic shell investment process, the complexity of castings that can be made in the process is very significant. We see here a wax pattern that has many complexities and fine detail in its structure. This inset shows the complexity of the aluminum tooling to make that wax patterns. An upper and lower half with slide mechanisms coming in from the side to create the cavities in the exterior profile. After the tree or cluster is thoroughly dried, it is heated, usually in an autoclave, to drain out the wax. The reclaimed wax is used for other trees and vents in the cluster, and new wax is used for the patterns. Next, the empty tree or cluster is put into a furnace and fired at high temperature to remove all residual traces of wax and take the pre-ceramic shell and turn it into a ceramic. The now ceramic shell is removed from the furnace and poured while the shell is still hot.
Next is Gary's case study, and he will highlight the investment casting's capabilities you've just seen applied to a highly specified, dimensionally demanding legacy casting application. In his case study, the importance of project management in those investment casting process capabilities will be the main message. One drawback of the investment process mentioned in September's Part 2 AirSet sand casting webinar is achieving high solidification integrity and high mechanical properties in the interior of a hot investment casting mold. The issue of investment casting radiographic integrity comes up in Gary's case study. And here's the reason. This small flow control valve made as a casting in a plain carbon steel. It's very complex in its interior passageway geometry, so being small and cored extensively, if it were an AirSet set casting, it would seem to be an ideal application for the capabilities of investment casting instead. However, there are significant interior regions of the mold geometry that are thick and difficult for carbon steel to solidify with high integrity if not fed for shrinkage and if remaining too hot too long. The consequence of an investment hot mold might be this casting leaking from one passageway to another inside those thicker, hot interior regions. There are ways around this problem, either by making the casting in AirSet with extensive 3D printed interior mold elements, or by changing the design geometry to feed those hot interior regions in the investment casting process. Those are the kinds of project management forethinking that is our webinar series subject. You will see the need for that project management thinking in Gary's case study.
Thanks, Mike. Now that we've seen how capable the investment casting process is, let's look at an interesting case study that illustrates how important immediate project management thinking is when producing a high specification casting. High specification legacy castings are not unique to the U.S. defense weapon systems. This case study involves a replacement part casting for a nationally known amusement park's roller coaster. Originally produced in the early 70s, this casting performs a high safety critical role in holding the coaster's vehicle wheels to the track when the G-forces are vertical. Our example is the set of wheels on the bottom of the track called an upstop, which is what the wheels do. Our case study casting is the bracket called a bogie that holds the upstop wheels against the bottom of the track rails, left side and right side. The combination of thin walls, tight dimensional tolerances, challenging solidification, integrity, and critical safety service makes this legacy commercial bogie bracket very much like a DLA legacy airframe casting. Amazingly, as of October 22, 10 legacy bogie upstop castings are about to be delivered to the amusement park after 1,250 working days over the course of 4 years and 10 months. The original quantity of 120 castings for the coaster system were produced as sand castings. The castings were made in green sand molds with all of the important thin wall and important as-cast dimensions formed with cold box cores in a complex core assembly, resting in a simple green sand mold cavity. Here's an image of what this type of mold looked like back in the day. This sand mold technology of years past could not have met the plus or minus 30,000 drawing tolerances on as-cast features required in the drawing. So the original engineering authority would have redlined the bogie bracket drawing to allow wider tolerances where the function of the bracket or its strength would not be affected, fit to air surfaces. But as a typical, those redline exceptions never get documented. The drawing tolerances remain the same. Although there have been no failures among the original 120 ductile iron castings over the 50 years, worldwide amusement park safety concerns have caused this ride's engineering authorities to tighten the castings specifications. Here are the major requirements increases that have resulted in more manufacturing difficulty. The Class 1 stamp on the drawing specified to the amusement park's internal specifications, and it conveys the overall message of stringent dimensional tolerance compliance and stringent solidification integrity. Certified radiographic testing is required. Solidification shrinkage must meet or exceed Class 2, which is difficult but doable. Cracks and hot tears must not be detected at all. Further protection against cracks or hot tears is magnetic particle inspection of the entire finished machine part. No relevant indications allowed. As cast and machine tolerances remain unchanged, and the possibility of exceptions has been precluded by the no reject casting it beyond tolerance. The first step in what would have been a project management plan for the 10 replacement bogey brackets was actually well thought out. The machine complete option using a wrought or forged bar is not practical for such a thin 3D design machine from stiff steel. The bar to encompass the bogey geometry would weigh 173 pounds to result in a 7-pound net shape. That means that 96% of the bar would wind up in chips. Also costly would be a series of very light machining cuts followed by stress relief heat treatment after each cut. Relieving the machining residual stresses is necessary to keep the thin walls straight. If the walls are not kept straight, subsequently cuts would make the walls too thin, and because the part would cause the part to be scrapped. The original cast ductile iron specification is obsolete, so the chosen investment caster requested an engineering change to allow 8625 low alloy steel to be substituted. 8625 was also chosen as economical to melt and resistant to hot tears. The basis for choosing the investment casting process is summarized in the table. For the bogey brackets overall, no exceptions, plus or minus 30 thousandths of an inch, as cast dimensional tolerance, the air set sand process would not be capable. The red arrow indicates the situation with the best possible tolerance being plus or minus 2 millimeters, which is plus or minus 80 thousandths of an inch. That's well beyond the allowable tolerance. The investment casting process has more than enough dimensional tolerance capability. The red arrow shows the consequence of thin wall straightness issues. The tolerance capability has been coarsened to plus or minus 0.4 of a millimeter. Converted, that is plus or minus a 16 thousandths of an inch, and still very good tolerance capability compared to the required plus or minus 30 thousandths of an inch. So to wrap up, let's look at what was not anticipated as it should have been by the two investment casting sources. In other words, what were the causes of delays and restarts from lack of careful forethought. Here is a table of initial manufacturing, engineering, and manufacturing processes choices and their problematic consequences. Printed PMMA patterns for the investment process is a common and worthy technology. However, the process is based on spraying a binder onto the wax-like PMMA polymer in the form of a powder bed. Normally, the powder bed supports hollow features and overhangs as they are being formed layer by layer. However, for very thin wall overhangs, the powder bed isn't sufficiently stiff to keep the thin overhangs straight. So among all of the PMMA patterns that were printed in attempts to make dimensionally acceptable castings, the printed patterns themselves varied widely in straightness. A capability study should have been conducted to determine the accuracy of PMMA binder jet printing at the onset. As we will see, a different, more dimensionally capable 3D printing process could have been chosen. At the time, the better choice would have been to build a traditional machine aluminum wax die and use traditional wax patterns. Here is the setup for pouring the bogey bracket castings and solidifying them to high integrity specification. Alongside is a 3D image of the interior thickness of the bogey casting bracket. The red thick areas shown in 3D are ridges where solidification integrity would likely be a problem. That concern has to be dealt with in the decision in the design of the tree and the wax pattern connections. Based on this mold setup, none of the prototypes nor 2 production runs of 10 castings pass the radiographic requirement. After the cancellation of the purchase order to the first investment casting source, a second source was launched in October of 2019. This table summarizes the project management thinking that was better and the manufacturing choices that were still not sufficient. Here are the highlights from that table. This second source has an in-house 3D printing machine capable in multiple materials, including actual wax. Included in the available printing materials is a support material that enables support structures to be built immediately under the thin wall geometry overhangs, so the machine can automatically alternate between wax and pattern in support structure as the print head transverses in the X and Y direction. Here's an example of intricate wax shapes, and the center example has a white support structure embedded below the pattern and inside the feature hand structure. This second source did what we have prescribed in our entire webinar 2021 and 2022 series. Made a prototype casting from 3 iterations of 3D printed wax patterns. Using those prototypes, adjustments were made to the solid model to correct pattern maker's contraction on a 3D basis and solidification movement of the thin walls. A second production run of 10 castings resulted in certified dimensions. Dimensions were certified on the basis of model base definition image of the solid model and a scan point cloud of the actual castings, one by one. The request for alloy change from 8625 low alloy steel to 17.4 pH high alloy steel is a consequence typical of investment casting producers. Unlike air set sand castings producers who are familiar with temperatures and mass gradients necessary to set up high solidification integrity, the hot investment casting mold produces the temperature gradients. Many of the alloys common to investment castings are not as sensitive to the mass gradients and directional solidification geometry as 8625 low alloy steel is. So the request to change from 8625 low alloy steel to 74 pH high alloy steel was unnecessary had the tree geometry been better conceived. However, the change made the existing mold setup for integrity more familiar to the investment caster, and it was successful in meeting the radiographic requirements. Here's the tree design and pattern orientation design by the second investment casting shop that was successful in 17.4 pH, but not 8625 low alloy steel. To have been successful in radiographic inspection of 8625 low alloy steel, here is what the tree design and pattern orientation should look like. Each of the thick sections shown before have been connected to solidification feed metal. To conclude, if you are a machine shop, cold start, new awardee for a similarly difficult DLA aviation legacy casting, you may be asking, how am I going to know all this stuff that's specific to the investment casting process, additive manufacturing, and alloy solidification differences? The answer is you won't. However, the benefit of project management thinking for the benefit of a machine shop new awardee is the questions that need to be asked among the manufacturing partners to avoid oversights. The questions need to be hard ones, and the answers can't be accepted if they are fuzzy. As the case study has illustrated, there were no reasons that the 10 certifiable bogey castings should not take longer than a few months, even as difficult as the requirements are. 4 3/4 years are the consequence of not thinking the manufacturing, engineering, and the manufacturing process through at the onset. The 4 3/4 years have been the consequence of mistakes and restarts.
As Gary and Mike have shown us, the investment casting process is very interesting in all of its facets, from making sculptures and fine jewelry to safety-critical jet engine turbine blades. Its capability to make dimensionally accurate surfaces with a fine surface finish and detailed cosmetics is unsurpassed among all of the metal casting processes. Implementing those capabilities is complex at the highest levels of component specifications, so project management at the very outset of manufacturing choices is necessary for success without mistakes and costly restarts. Those manufacturing choices include how to make patterns to be invested in the ceramic shell. Should it be traditional machined aluminum dies into which the liquid wax is injected? Or should we use 3D printed wax equivalent patterns directly from a version of the design's solid model? If 3D printed, will the 3D printing process be dimensionally stable enough to make dimensionally capable castings? If high stress areas reside in the interior of the casting geometry and designated areas for higher mechanical properties are specified in those locations, will the hot investment shell mold cool those locations quickly enough to meet the required mechanical properties? If not, the air-set sand process may be required instead. Is the investment caster chosen capable of advanced project management planning? Is there evidence that the investment caster has made these kinds of plans in the past? If those choices can be made affirmatively, then the investment casting process is a great choice for high specification castings, including castings for DLA legacy weapon systems. Our final part 4 of this project management walkthrough of machining and casting process choices addresses the casting finishing processes common to both the air-set sand and investment castings. Finishing processes are where the casting's dimensional capability and consistency for machining setups can either be sustained or upset. It is an important subject that's not often addressed, and it needs to be addressed in the same advanced project management planning as the choices of the casting process and tooling design and construction. The webinar Part 4 broadcast is scheduled for Wednesday, November 16th. I will send out an email invitation in advance as well as a broader webinar announcement email. And now, let's go to the chat box for questions and a couple of discussion topics.
This part. All right, so I'll just go through and introduce the CAST-IT team members who are on the line. So we have Mike Wynn, who you met in the video. He is an expert in all things manufacturing engineering as well as casting design. We have Gary Burrow, who you also met and just popped up on the screen. He is a 5th generation pattern maker and really all around casting guru, knowledgeable in all the processes as well as materials. And then we have Keith Sturgill, who is a metallurgical engineer, and he is really the guy you want to go to if you have any questions about DLA processes or anything along those lines. So I was thinking to start off to give you guys a chance to type in any questions you have in the Q&A box. We'll go ahead and start off with a poll. So this is just 3 quick questions. I'll go ahead and launch it now and everyone can answer. And we'll give you guys about 3 minutes just to go through these. If you don't know the right answers, pick what you think is correct, and then we'll go through the answers. But while you do this, feel free to type in any questions you have. And I muted myself. It looks like we're still having a couple people answer, so I'll give you guys another minute here, and then we'll go through the answers. All right, so I'm going to end the poll, and then I'll share the results with you guys. So everyone should be able to see these. Mike, I wanted to see if we could just kind of go through the questions and talk about the answers. So for the first one, we have choose which are significant attributes of investment casting process. So could you just go through that one?
Yes. The investment casting process, as you saw in that video and description, is not fast. So it's, really is applicable to low volume legacy requirements because it isn't very fast, but it is highly accurate. Its surface is really what it makes the process so capable, not only dimensionally, but also in terms of as-cast detail, fine lettering, and smooth surface finish. And it really does have the most directly applicable use of additive manufacturing technologies to make a tool directly that's equivalent of a wax pattern and go directly into the process with really no other considerations other than just simply making the tooling directly from additive manufacturing. So with regard to the true and false, it really is the oldest metal casting process as far as we know, based on historical records and archaeology. And most people don't realize that jewelry is almost always made from the investment casting process. So that's an interesting facet, as is all the bronze statues going way back in history as well as currently. And since it is a slow mold making process, it's more difficult to accommodate high volume, but high volume parts like jet engine turbine blades are made that way, but it's more difficult to accomplish that. And it is capable of large castings. If you notice during the description of the process, there was about a 4-foot diameter fan frame made in titanium, and there was a woman wax welding the blades into that stationary fan frame for like a 767, 757 jet engine. And those are about 4 feet in diameter. So investment castings can be very big. The next one, let's see. Yeah, there it is. With regard to advanced planning using project management, it really does just avoid the trap of just starting as if you're doing something like you always do, because on these complex legacy castings, you just can't afford to go down the usual path and keep making mistakes. As Gary's case study shows, it's just a killer in terms of cost to the producer, and then of course lead time to the people who are needing these parts. People would not be impressed by out in the shop by maybe your project management planning, but it really, really does help them as well. And it does make you think through in advance what's required before you get started. And it does also help you see better what needs to be done in sequence. And it doesn't just make you look busy while you're not doing anything.
All right. So you kind of touched a little bit on the fact that investment castings, there's a wide range of parts you can make, from jewelry to these highly stressed, safety critical items like jet engine turbine blades, as well as the fact that there's a huge size range. So one of our questions, I think that's kind of related, is it seems like this is good for everything. What is it not good for? When would using investment casting process be a disadvantage, or when would you not want to use it? Mike or Gary, do you want to take a stab at that?
I'll take a quick comment and then let Gary fill in the blanks, because Gary is a real pro with this. It's those hot interior sections. When the mold is that hot and you've got thicker sections in an alloy like 8625, and that's what went wrong with the first supplier, and even to some extent the second supplier on that amusement part upstop bogey casting. Those interior sections that were hard to reach in the investment casting process wouldn't solidify with that really, really high solidification integrity and the high mechanical properties required. So when you have those hot interior sections and a hot mold in an alloy that wants to solidify directionally, which means it's sensitive to those internal hot areas, both size-wise and temperature-wise, well, then you have more difficulty in getting the investment casting process to work. Doesn't mean you can't, but you have to think about it a lot more. And that's where the investment or the air set casting process sometimes is specified for that reason. So Gary, fill in the blanks for me there, buddy.
Well, I think you hit it pretty good there, but the integrity of the casting is one item, and also the cost. Investment casting is an expensive process. Sand casting is an inexpensive process. So you use it where you need it. You know, if it needs to be investment casting, make it. If you can get away with sand, it's a much more cost-effective direction to go. And all the variety of sands that we have also, air set, green sand, core packages. It's a lot of ways to get there. You just got to make the right choices. So I think that should be pretty well covered.
Yeah, those are points we didn't make, Gary. Good thinking.
Cost is always a factor. And I will use this as a shameless plug. Mike did mention the air set sand process. We do have a webinar on that as well that we've already done, but there is a recording available online. So I will be sending out the link after the fact for this webinar, and I will include that as well, but I'm going to put it in the chat too, just in case you guys have not had a chance to check that out. All right, so one more question, Mike, just because I'm a little curious. Like I said, it really is hard for me to believe that this investment casting process can be used for something, you know, as pretty as jewelry, all the way to something that's safety critical. How can we make those safety critical parts like the jet engine blades using the investment casting process?
Well, on that one, I'm going to defer to Keith, because Keith is a jet engine guru and he knows how this actually works. He's told me how it works. I'm going to have him tell us how it works for sure.
Okay, Mike. Well, one thing about turbine blades that if you're familiar with jet engines, you understand, and if you're not, it could be interesting to you. Turbine blades in particular, they spin very high RPM and in very hot temperature. So as the modern jet engines evolved, they wanted to get more power out of them, thrust to weight ratio. And the way to do that most easily, I guess, or most directly, is to increase the turbine inlet temperature. In other words, the engine runs hotter. Well, as the turbines ran hotter, you began to see a failure mechanism called creep. And creep is basically just stretching under a tensile load, radial tensile load at high temperature. So creep, as they studied it, they learned that creep would start at the grain boundary intersection points. They call them triple points. So the engineers and material scientists needed to move away from structures that had a lot of grains in them. And first they went to directionally solidified, which was columnar grains, which oriented from the root to the tip on the blade. And then they evolved to single crystal. So your entire blade is one crystal, one grain. So they developed procedures to do that. And the best way that they came up with, they tried a lot of different things, heating coils that transversed as the part solidified and that sort of thing. But the most successful was having them solidify from the tree up to the through the gating up to the tip. And so, Julia, your question is, how can they make safety critical structures this way? Not exactly sure how to answer it, except other than through very close process control. They've achieved a way to directionally solidify and actually have single crystal blades. So these items are performed very well at high temperature, high RPM, high radial stress applications like turbine blades. I hope that answers your question.
I think it does, Keith. That's really interesting background on the evolution of kind of the design of the turbine blades and how that's made. So Mike or Gary, did you guys want to add anything?
Well, I think one of the other things I think most turbine blades are made that way now, as they've gone to an additive manufacturing process where they're actually printing the ceramic cores that are the cooling inside of the vane. And they're small, I mean, 30, 40 thousandths in diameter in some cases, and they lay those cores in there and then cast those, and that's the only way you're able to cool those blades enough to be able to increase those high temperatures without melting the metal.
Yeah,
That's
Gary,
a really good. Excuse me, Keith. Go ahead.
yeah, that's a really good point. I overlooked the internal cooling passages that are also critical to the performance. You have to have that bleed air pushed through the internal cooling passages of the turbine blade for it to cool the blade some, so that they can achieve those higher turbine inlet temperatures. And as you said, I think Honeywell had and Dean, I think's on. He actually funded that work.
Right.
Honeywell was printing the ceramic cores for the casting molds, and these cores provided the cooling air passages internal to the turbine blade. Good point.
Julia, my only comment that I would make in addition to what Keith and Gary have described so well is that when we're all sitting inside the passenger compartment of a commercial aircraft, and the engine is like right outside the window next to us, think about Keith and Gary, because of what they just said, we're safe.
Yes, you can definitely rest easy knowing knowing there's some capable guys behind the scenes.
Yeah, it's not just keeping the plane in the air, it's keeping those blades from flying through our window.
All right, so it looks like that was the last question. There's nothing else in the Q&A. So I am going to put a link to the survey for this webinar. Please fill it out. We really do value your feedback, and it's only, I think, 3 or 4 questions. It'll take you less than a minute, so please do that. And then in addition to that, if you are attending this for a CLP credit, I'm going to put my email address in the chat as well. Please send me an email and I can get you a certificate if you need one to show that you attended this. So with that, I just want to remind everyone that we will have part 4, which is the final part of this project management approach webinar series. That will be November 16th at the same time, so 11 Eastern. I'll be sending out a email announcement for that with registration information, as well as a flyer if you would like some additional info on what that'll cover. And if you have any questions about the content that we discussed today, feel free to reach out to me and I can get you in touch with the rest of the team. But with that, thank you guys for participating in the webinar. All right. Bye, everyone.
Thank you.
Bye.